the last minutes that I have, I would like to spend on the last three parts. So the first one is now a DG-HGG splitting. So 30 minutes, huh? Yeah. Okay, so what is the idea now? So before, in the Navier-Stokes example, we already saw a very cheap or very simple way to set up a timeless stepping scheme, where we decided to set up this M-star matrix for the instationary Stokes problem and do an explicit scheme for the convection application. Now we want to do something similar and now improve in certain aspects. So here we want to change the spatial discretization. So we want to go away from the H1 conforming setting that we had in the second tutorial in this section, but we rather want to go to something DG-HGG. I will explain this in a minute. And furthermore, we want to also do something a little bit different in terms of the operator splitting, or in splitting these operators in terms of explicit and implicit. So what we want to do is a Yanenko type operator splitting. So we solve this problem. So the operator here stands for the Stokes part of the problem, and the operator C for the convection part. And what we want to solve now is we want to solve in a series. We want to first solve a problem that does not involve the Stokes part, so just the convection part for some time step Tn to Tn plus 1, which gives us an intermediate solution. And then starting from that, we apply another time step from Tn to Tn plus 1 for the implicit solution of the unsteady Stokes problem. Okay, so this is not the best discretization that you can do, of course, but this tutorial is meant to show some components based on this discretization. Okay, so for the discretization, we also want to do something more fancy than just Taylor-Hood. So we use something which is HDiff conforming, because HDiff conforming is very cool. It's very nice, has very nice properties, and especially for Stokes and Navier-Stokes, there are very nice properties which lead to certain robustness and flexibility of this method. So what we want to do is a DG formulation based on an HDiff conforming finite element space. I want to combine this with an upwinding with respect to the convection. And because of we want to solve the linear systems for the Stokes part, we don't want to use a standard DG discretization, but as we learned before, doing something like an HG discretization is cheaper. This is what we want to do in this tutorial here. So geometry is the same as we've seen before already. So this is the Schäfer-Turek geometry. And now the HDiff finite element space we also saw. The overall discretization for the velocity is, however, a little bit more complicated. So we now have an HDiff conforming finite element space. So we are non-conforming with respect to the H1 regularity that you typically have in a Stokes, and especially in a Navier-Stokes problem. So what we have to deal with is incorporating tangential jumps weakly. And this is what we do with a new space, which is called the vector facet space or tangential facet space, which are polynomials that are just defined on the skeleton, so just on the facets, and are in tangential direction. Yeah, so like the trace of an H-curve conforming finite element space. Okay, and the corresponding fitting pressure space to that is just obtained by taking the divergence of the space, which just means you take a piecewise polynomial discontinuous 1 degree less. Okay, and this is the space, so we have an HDiff space of a corresponding order with corresponding boundary conditions. You have a vector facet AV space of the same order. You have one order less for the pressure space, and you put them together in one product space. Okay. We also have here the tangential projection involved, which is just on every facet subtracting the normal components, which we'll need in the formulation. So what you see here is now the formulation of the viscosity and the divergence constraints put in one bilinear form. So if you just consider the first integral and the last three ones, this is the vector valued version of the interior penalty, or the hybridized version of the interior penalty method that you already saw in Unit 2.8, where Joachim discussed DG discretizations, and then you have the corresponding gradient of the pressure and the divergence constraint in here. Okay, so this is what we define here. So think about this in the H1 conforming world. This would just correspond to those three integrals here for the Taylor-Hood, and these guys here are now necessary because we don't have the tangential conformity anymore. Okay. We set up the corresponding mass matrix for this guy, set initial conditions, solve the Stokes problem. So this is what we know already. And now the question is how to do the time stepping. And for that, we wanted to have first solve a problem that just involves the convection, so not the Stokes parts. And we want to do this actually on the DG space. So there's no point in doing an HGG discretization for this because it's completely explicit, so we don't have this drawback of additional couplings that we have in HGG methods. Okay, so we want to apply a method as before, but we have to make the spaces that we use compatible. So we have to map from the HGG space, so this product space out of three functions, we have to map this into an L2 space, which is simply what we saw already in the other examples, and then apply the operator there and project back into the other space. Okay, and here we can do this by formulating mixed bilinear forms for the transfer operation, or you could similarly do something like the L2 convert L2 operator that we saw, that we also discuss in a minute on the slides. But kind of the straightforward way to do this is the following. So we have now the vector L2 space, which is the space in which we want to apply the convection operator. And then we have this mixed bilinear forms, which involve functions from the product space of the complicated Stokes discretization and the L2 vector L2 space. Okay. Yeah, we apply those two and want to apply standard convection discretization by upwinding. And we also know that we have as the velocity field, we have this H-diff conforming velocity already, which is pointwise divergence free because it's a solution of Stokes or unsteady Stokes problems. Okay, this is how it looks like. So we just have, so these lines here, the whole block corresponds to the vector valued version of the upwind discretization of the convection. So this is something that we know already from before. And now we have a new matrix operator, or a base matrix operator, which should solve this convection problem for a certain amount of time steps. So we want to solve for tau, so for Tn plus 1 minus Tn. We want to solve the problem, and we allow to apply several sub-steps to go from the one to the other. For example, to meet stability conditions. So in the constructor, we essentially just define some functions, for example, the mass matrix, the inverse mass matrix operations, and so on. And then in the actual operation, we first, and this is kind of what was important, so the first line, the input of this is now an H-diff, or it's actually from this product space, from the Stokes discretization, it's a vector X. And now the BF mixed matrix is now the application of this guy from the previous slide. So here we define this mixed bilinear form. So the result of this application is now functional in the L2, in the vector L2 space. Now by now applying then the mass inverse of this space, we essentially have the representation of this H-diff vector as an L2 function, or vector L2 function. So this is the result here. And then on this, we just apply the standard, or the simple explicit order scheme in a similar manner that we saw before. Yeah? So we have the convection application, we have the inverse mass matrix, some sub-time steps, and so on. And then if we have the solution after several time steps in the L2 space, we project back into the H-diff or in the product space, which is then happening here with the BF mixed transpose. Okay, so putting this now together, we set up the M star matrix for the unsteady Stokes part of the problem, and the overall time loop now takes this form. So we have the proper rate convection operator. So this was the base matrix that for which we defined the matrix vector, or the operator application. We set a number of sub-steps that was defined before, I think 10 or something like this. And now this is the overall application that we get. So we have essentially applying this 10 sub-steps, obtaining a residual vector from that, and solving the unsteady Stokes problem for this. So it's an implicit order for the Stokes part, and several steps of the explicit order for the convection step. Okay. And with that, we can now solve the problem as before, with the benefit that the stability restrictions are a little bit better than if you would just apply the IMAX scheme that we had before. Okay, so the idea of this tutorial was essentially to discuss the operators between the different spaces. And instead of doing this with the mixed bilinear forms, you can also do this with the convert L2 operator that also Joachim mentioned before. So this is what you have here. So you can directly write down this operator going from the HGG space, or the Stokes discretization space, to L2 by first applying the embedding. So just take the HDiff part of the whole vector and then convert the HDiff function into an L2 function. So this is what gives you that operator here. And then the corresponding new multiply operation of this propagate operator takes this form, where we essentially just have now the HGG to L2, which replaces the mass matrix inverse and the mixed bilinear form applications, and the same also for the result vector here. Okay, and then we can do the same as before, so continue with a few other time steps. All right.